Okay, here's a classic mathematical card effect involving a 12-hour clock. Now, Matt's handling of this effect is different from mine. I'll have his playing in the background, but I'll show you how I prefer to do it. So I'll have his linked in the description below. So if you'd like to watch his original version, it will be there for you to watch. But for this effect, you need 13 random cards chosen by the spectator. And then have the spectator mix those cards as much as they would like. When they're satisfied with the mixing, have them cut off any number of cards from that pile of 13 and to hide those cards somewhere in a pocket or under the table, okay? And so we'll bring those out in just a moment. Now what he does is he has the spectator, after mixing these cards further, note the identity of the bottom card, which is great. So it's a 4 of hearts, I believe. And then this packet is set on top of the rest of the deck, okay? Now from here, he goes into creating a clock configuration immediately. That will be a little different than what I'll do. So he's going to build a clock starting at 12 o'clock and then going backwards, 11, 10, 9, and so forth. Okay, so 12 o'clock, and he has the clock facing us, the viewer here. 10, and then 9, 8, 7. In fact, he builds a much tidier clock than I probably will. Maybe he practiced a bit to get it nice and symmetrical here. Okay, and then the final card for 1 o'clock. Okay, and then he says, well, why don't we go ahead and take a look at the cards that you cut off at the very beginning, now that we know how the clock is constructed. Okay, so you have them grab those cards that they ran. You have to realize it was a random cut, and have them count the number of cards that they randomly cut. Okay, and I believe it's 7 cards. Okay, so what you do is you say, well, 7, well, that means 7 o'clock for us here. So why don't we count to 7 o'clock on the clock? So we have 1 o'clock, 2, 3, 4, 5, 6, 7. Okay, where does that bring us? Right to the spectator's card. Absolutely amazing. That was a free cut by the spectator, and somehow they were able to find their card. Amazing, amazing. Okay, so that's Matt's presentation, which is a great way to do it. But like I said, I'll do it a little bit differently. First off, I want to point out that I'll have in the description below a link to a video called Magic Clock, in which I go through the mathematics behind this effect. But what I'm going to do here is I'm going to show you a different handling of this effect that I think is easier to remember and a bit more intuitive. So what I've done here is I've selected 13 random cards, but they're blue back. Okay, so that's going to enable us to essentially look under the hood to see why this works. And then if you're interested in a mathematical proof and explanation of why it works, I have a write-up right here, and then I'll point you to the video that I've linked below that I've mentioned already. Okay, so let's kind of dissect this and see what's going on with it. So these are representing the 13 random cards chosen by the spectator, and we'll be able to spot them mixed in with the red, of course. Okay, so these can be mixed thoroughly and so forth. So the spectator cuts off any number of cards, and we'll set them right here for later. Okay, and then they need to remember the identity of the bottom card. Now I think what we'll do here is we'll go ahead and just have that face up so that we can kind of watch it. And then I'm going to set it on top of the rest of the deck. Now, of course, when you go to do this, you don't have 2 colors of cards that you're working with, right? This is just for educational reasons, right? Okay, and then my handling goes as follows. You just deal out to the table first 12 cards for the 12 hours for constructing the clock. So you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 cards, okay? So these cards are now reversed from what they were before and in the reverse order to what Matt did. Okay. Now all we do is we just deal them out. So 1 o'clock, so we deal to 1 o'clock first. We just deal them out in the normal order that you would deal out cards to create a clock, right? 1 o'clock, 2, 3, and then there's 4, then 5, 6 o'clock down here, 7, 8, 9, 10, I'm going to go off, 11, and then 12 up there. Okay, sorry about that, but that's 12 going off the screen there. Okay, and then you just turn to the spectator and say, okay, let's see how many cards that you randomly cut off. Okay, and so you can have the spectator openly count those 1, 2, 3, 4. So 4 were randomly cut. And then you just tell them, I think those 4 cards are telling us something. I think if you go to the 4 o'clock hour on our clock, we might discover something interesting or surprising. Okay, and now you can see what's going to happen. 1 o'clock, 2 o'clock, 3 o'clock, and then when they reveal the card in the 4 o'clock position, it will in fact be the card that they noted at the beginning. Okay, so you can kind of see it working here. Now the important thing is, why does this work from an intuitive point of view? So let's just look at kind of an informal discussion or justification for why this works. And then if you want to understand the precise mathematical proof for it, then I'll point you to that other video. And you can even take a screenshot of my write-up because it explains it as well. Okay, so let's just think about this for a moment. Let's say, so they cut off 4 originally. Let's say they had cut off 1 more card. Well, think about it. If they had 1 more card when we were dealing all of these, right? Remember how we were dealing them? The final card that we dealt was this one. So if they had retained 1 more, that one wouldn't be there, right? In fact, what that would have meant is we would have picked up another red card, right? To get up to 12. For this number to be 12, we'd need 1 more red. Well, all that does, so just look at what that does. This card would no longer be in the 11 o'clock position. It would be in the 12 o'clock position, okay? For the simple reason that we would have had 1 more red card, which are being dealt to the table first. So this would have been 1 o'clock. So it's almost like you're just rotating the clock by 1 hour. That's all you're doing. And then this rotates to the center like that. Okay. And so now that we've cut off 1, 2, 3, 4, 5, count again, 1 o'clock, 2, 3, 4, 5. So it doesn't matter how many cards are in this packet. What it does is it increases the number of red cards that you're going to need to get up to 12. And that has the effect of just rotating the clock 1 hour for each additional card, red card that you need. Okay, so that's why it's working. This number of cards is exactly tied to the position of that noted card at the very beginning. Okay, very, very cool effects. Okay, so if you're interested in understanding really the proof for it, why does it always work? I tried to just kind of convince you that it makes sense intuitively. But here I've used something called Norman Gilbreth's bracket notation. So this mathematical way of describing what's going on in this particular card effect, this is notation that Norman Gilbreth invented, and that's the same Gilbreth who discovered the Gilbreth principle. Okay, and so I've given a full proof of this effect using Gilbreth's bracket notation. And this will tell you that, in fact, this card here, this is the spectator noted card, the red one with an asterisk, is going to be in position X, where X is the number of cards that was freely cut. Okay? So this is the packet of cards cut by the spectator and hidden away. And then at the end of the proof here, we find that there'll be X minus 1 cards above the spectator's card, which means you'll go 1, 2, 3, 4, 5, 6, and then you'll get up to X minus 1, and the next card will be the spectator's card, and it is in position X. So the Xth position of the clock means that the number of cards that they cut, which is equal to X, will actually locate the position of the spectator's cards within this 12-hour clock. Really cool. But if you're wanting to understand this fully, take a look at that link in the description below because I go into Gilbreth's bracket notation in depth and show you how you can use it to prove not only this effect, but several other classic card effects, like the 21 card force. If you've heard of that before, the 21 card force can be easily proven to work and be true using Gilbreth's bracket notation. So thank you for watching, and take a look at other videos on the Absolute Math Magic channel.